All right, so now we move on to lesson 6.4, which is rational equations part 1. We're going to be solving for specific x values given rational expressions that have some sort of equality. So in these problem solvings, again, what we're going to want to do is make sure we factor them completely if possible, because if we factor them completely, that's going to help us establish the LCD. Once we can establish an LCD, this helps us eliminate the fractions. So the lowest common denominator, if we can multiply to all the terms, it's going to eliminate all fractions that are available. Once we're able to eliminate the fractions, then we can solve for the specific equation or solve for the specific variable in the equation. And then lastly, we can always just verify by plugging our answer back into the original and seeing if the two sides are equal. So let's look at the first example here. In this first example, I have the following where 2x plus 1 over 3 plus x over 4 equals 5x minus 1 over 6. Well, in this situation, I want to establish the LCD right away because I can't really factor it and there's no restrictions. So I look at this and I go, well, the lowest common denominator for this one, the first number that 3, 4, and 6 all multiply to is 12. So once I establish that my lowest common denominator is 12, well, what I'm going to want to do is just rewrite out the terms. So 2x plus 1 divided by, and let's just clean that up a little bit, 2x plus 1 all over 3 plus x over 4, which is equal to 5x minus 1 all over 6. Now from here, we're going to multiply everything by 12. So I'm going to surround all the terms on the left, all the terms on the right, and multiply them by 12 and 12. Once I multiply them by 12, I'm going to distribute this to all the terms. So 12 divided by 3 is 4, which I can rewrite this as 4 times 2x plus 1. I can then go, well, plus 12 over 4 is 3x, because x is the only term there. 12 divided by 6 is 2, so I'm going to rewrite this as 2 with 5x minus 1 inside the bracket here. Now I want to expand this. This will become 8x plus 4 plus 3x is equal to 10x minus 2. Now from here, what I'm going to do is go, well, 8x and 3x make 11x's on my left-hand side plus 4, which is equal to 10x minus 2. And now from here, I'm just going to make sure that I distribute, or not distribute this, but I move the terms appropriately. I'm going to take the 10x from the right and move it to the left. Reason being is that I want to keep the x's positive, and this does it for me. That means I have to minus the 4, the constant term, over to the right-hand side, and then I'm going to get the following, that I have 11x minus 10x is 1x, which is equal to, on the other side, we have negative 2 minus 4, which gives us negative 6 as our answer. Perfect. Okay. So now once we've established this, and we just want to double check everything seems okay. Yeah, it looks good to us. So we end up getting that x equals negative 6. Well, if x equals negative 6, let's just make sure we plug it in on both sides and then see if we get the same value here. So what I'm going to do is I'm just going to go over to our step number 2, as we're going to call it. So maybe we list this as number 1, actually getting the specific value. Once we get the specific value, then what we're going to want to do is combine them together. So I go over here and I'm like, well, for step number 2, let's go to our original equation and plug it in. So it's going to be 2 times our negative 6 plus 1, all divided by the 3. And then we're going to go plus our negative 6 over 4. And then this will lead us to, on the other side, 5 times the negative 6 in the bracket minus 1, all divided by 6. Now what we want to do is we can just type these things in. So, I mean, we could do a little bit of simplification just to help ourselves out here. So 2 times negative 6 is negative 12. Negative 12 plus 1 is negative 11 over 3. Then we're going to add the, or I guess we could just even subtract the 6 over 4, because if it's a plus minus, which is equal to, we have 5 times negative 6 is negative 30, minus 1 is negative 31 over 6. Okay, now we just want to confirm that this left-hand side is equal to the negative 31 over 6. So I'm going to bring out my calculator here, and we're just going to type that in here. So we're going to go math frac negative 11 over the 3, and then we're going to go from here minus 6, and maybe I should type in that fraction key, 6 over 4, which I guess we could have reduced to 3 over 2 if we really wanted to. This gives us this, we convert it to a fraction, and we end up getting negative 31 over 6. So it does work. Perfect. So what I'm going to do here is I'm just going to write this as negative 31 over 6, which is equal to negative 31 over 6. And if this is true, my left-hand side is equal to my right-hand side, and I think that this is good. As soon as you can prove left-hand side equals right-hand side, we see this as a strong verification. And then what we can always do is just go back to our solution, make sure we highlight it here, and that will be perfect for us. Okay, now when solving rational equations, what we want to do is we want to make sure that we have at least one rational expression, so that should be pretty obvious. And then to solve them, we're just going to go through the same steps that we've done before, but just add this element of an LCD and how it contributes to eliminating this fraction here. So let's just quickly go through the steps. We're going to fully factor each denominator, of course, because we want to make sure what the factors are. We want to identify the non-permissible values from our factors, determine the lowest common denominator, or LCD, write each rational expression as an equivalent expression with that LCD, multiply both sides by the LCD, and then solve and check and verify that your solution is there. Now, let's take a look at our first situation here, our first example where we look at one with a variable in the denominator here. So what we're going to do is we're going to take a look at the situation where we have an x right here. If there's an x in the denominator, what I want you thinking is, okay, well, we know that at least one of our MPVs, because it can't factor any further than this, we're going to write our MPV, and maybe we do that off to the side here. I'm going to write it just here. Our MPV is where x cannot equal 0, because if x equals 0, then it takes out this denominator and it makes this not a real number. And so we look at this, or it makes it undefined to be more specific. So we want to make sure we account for that. Now we want to state our LCDs. So I'm going to do that right here, just below the problem. Our LCD, well, the first thing that 4 and x multiply to are 4 and x. So we have to multiply all the terms in this equation by 4 over x, or 4 times x, sorry. So I'm going to write this as x minus 4, 7 over x, and then this is equal to 3. Now, let's surround both sides of the equation in brackets. I'm going to multiply by the LCD to both sides, so to my left and right hand sides. And here's what's going to happen. When you multiply by the LCD, you're going to notice that the denominators go away. What is 4x times x over 4? Well, the 4's go away, and this just leaves me with x squared. I then can multiply 4x times 7 over x. Well, the x's are going to cancel because 4x over x is just 4. 4 times 7 is negative 28, which is equal to, on the other side, we have 3 times 4x, which is 12x. Awesome. Okay, now what we're going to do is from our quadratic equations unit, we knew to bring this 12 across. So I'm going to go minus 12x and then minus 12x because we want to keep our x squared term positive. This is going to end up giving us x squared minus 12x, and then let's make sure that's just a touch neater there. Minus 28 is equal to 0. Now from quadratic equations, we know to factor this thing. If we want to get specific x values, we got to make sure we plug them in. So I'm just going to carry forward up here, and I'm going to say, well, if we know we have x squared minus 12x minus 28, then if I bring this up here to continue solving this, what we're going to do, and I'll just make it a tiny bit more curled there, perfect. We're going to factor this and say, well, things that multiply to make negative 28, but then add to make negative 12, we want to be thinking about things like 14 and 2. Those are probably our most ideal numbers. So I'm going to write this as x minus 14, and then we're going to write this as x plus 2. Because if I multiply these two together, I get the negative 28. I also add to make the positive 12, and then we're happy with this, or the negative 12, I should say. Now, from here, this means from our quadratic equations unit, it's always opposite of whatever you see in the brackets. So this is x is 14. We have x is equal to negative 2. Now we have two values, but we have to make sure that these actually work because who knows, maybe one of them doesn't work and it must be extraneous. So we're going to confirm that here. What we're going to do is, realistically, you could type this into your calculator and see if they overlap. The other thing you could do is just directly plug them in algebraically. So again, if this is step number 1, which is determining the NPV, the LCD, and then creating the actual X values, then step number 2, we're just going to verify it. So I'm going to go maybe starting right below this. We're going to try and verify them separately or independently, and I'm going to plug it back into the original here. So my first X value was 14 over 4, and then minus 7 over 14 is equal to 3. I'm just going to simplify this a little bit. They both divide by 2. This is 7 over 2 minus, they both divide by 7. So this is 1/2. There we go, is equal to 3. Now, 7 minus 1/2, well, 7 over 2 minus 1/2, that's the same as 6 over 2. And we know 6 over 2 is 3. So this gives us 3 equals 3. And the left-hand side equals the right-hand side. So I'm going to try to squeeze that in there. Left-hand side equals the right-hand side. Therefore, we know that 14 is one of the solutions. So that's good. Let's just confirm with our other one here. So in the same equation, I'm going to put in my negative 2 over 4 minus my 7 over the negative 2. which is equal to, on the other side, the positive 3. Well, this is the same as negative 1/2, and then plus 7 over 2, and then this is equal to 3. Well, yes, fortunately for us, again, this is the same as 7 over 2 minus 1/2. So this gives us 3, which is equal to 3, or the left-hand side is equal to the right-hand side. And again, you prove this or you verify this, and then that means you can highlight both, none are extraneous, and we feel happy with that. But again, you wouldn't know that until you verify it. So I highly recommend that once you actually solve for those values, just make sure you verify it quickly, just so that you have the full comprehension of this. Okay, let's move forward. Now, let's say I'm given something like this. Now, this isn't as straightforward, right? Because we see it and we're like, okay, we must factor it. We see a couple binomials, we see a trinomial. It's going to be important we factor this. So I'm going to rewrite this as the following. This is going to be 9 over y minus 3, and then this is going to be minus 4 times the y over 6, or y minus 6, I should say, is equal to, in the numerator here, 18 over, what multiplies to make 18 adds to make the negative 9? Well, we think about things like, okay, well, we have 6 and 3, and I think 6 and 3 is going to do it, because if we have y minus 6 and then y minus 3, the double negative will multiply to make the positive, and the double negative will add to make the negative 9. So we're happy with this. Now, this actually means a couple things for us. We want to state the NPVs as soon as we factor. Y cannot equal two values here. First one is 3. The second one is 6. If y is equal to 6 or 3, it's going to wipe out these denominators and make these non-defined functions, or non-defined in terms of the overall equation and rational expressions. So we want to make sure they're defined. So we have to have values that are not 3 or 6. Now what we want to do is we want to multiply everything by the LCD. Now, in this situation, we could even write this maybe, I'm going to write it over somewhere here. I'm just going to put like a arrow here and be like LCD. What is our LCD? Well, we've discovered that it's actually the two binomials, y minus 3 and y minus 6. If we have y minus 3 and y minus 6, if I multiply everything by these terms, then therefore I'm not only going to get at the common denominator, but I'm also going to be able to wipe out these denominators. So let's do that here. I'm going to surround both sides of the given equation, or the rational equation, in brackets. I'm then going to multiply by the y minus 6 and y minus 3. And I want to make this as neat as possible just so we can see all the terms appropriately. There we go. So y minus 6, y minus 3. Again, over here, we're going to go y minus 6 and y minus 3. Now, the reason we multiply by both is because it needs to apply to every term. Now, from here, what I'm going to do is apply both of these binomials into each term. So when I distribute this, well, if I distribute it to the first one, we notice that it ends up canceling the y minus 3's, and I actually just have the following. This is going to be 9 times y minus 6, because the y minus 3's cancel. Same thing for our next ones. We see that the y minus 6 is a shared term, y minus 6 over y minus 6. That leaves me with y minus 3 times the 4, or vice versa, 4 times y minus 3. This is going to be equal to, on the right-hand side, well, they both share the same binomials, and so we wipe out that full denominator of the two binomials, and this becomes 18. Now we're going to expand this. This becomes 9y minus 9 times 6. This is where, you'd always want to have your calculator just in case, 54. And then we have minus our 4y plus 12, which is equal to 18. Now, if this is equal to 18 on the right-hand side, now we want to combine our terms. 9 minus 4y is 5y. And then combining 54 and 12, we're going to end up getting negative 42. There we go. And then this is going to be equal to 18. We want to add that 42 across because we want to isolate for the 5y here. So I don't want to add 5y. I want to add 42 to both sides. Then from here, this is going to give us that 5y is equal to 18 plus 42. That's the same as saying we have 20 plus 40, which is going to be 60. And then we want to divide both sides by 5. As such, there we go. And then we're going to end up getting that y is equal to 12. Perfect. Okay, now if y equals 12, we just got to verify that this is actually the number that we can plug in here, right? Because we never know if it's extraneous. Let's just double check with our NPVs. Nope, it's neither 3 or 6, so we seem happy with that. But we also want to just make sure that it actually applies here and that we end up getting the exact same thing. To do that, what we can do is we can just verify it off to the side. I will go somewhere over here and just verify it. So in this gap here, let's just make sure I got my right fraction. So it's going to be 9 over y, which is 12 minus 3, minus my next term was 4 over 12 minus 6. And then this is going to be equal to, on my other side, I had 18 all over y squared, which is 12 squared. In the denominator of this one, minus 9y, which is 9 times 12, and then plus 18. Okay, let's simplify what we can. So 9 over 12 minus 3, which is the same as 9. 9 over 9 is just 1. And so I'm going to write this as 1 minus 4 over 12 minus 6 is 4 over 6. That's 1 minus 2/3, which is equal to, on the other side, I'm going to try to simplify this as much as I can with the help of my calculator. So if I have 12 squared, that's 144. 144 minus 9 times 12 is equal to, and then I add 18 to that, is equal to 54. So this ends up giving me that it's 18 over 54. 18 over 54, let's just double check the reduction here, which it should match 1/3. So this is perfect. 1 minus 2/3 is 1 over 3, which is equal to 1 over 3 as a reduction, and therefore my left-hand side is equal to my right-hand side. As soon as you see that this is true with the verification, you're like, hey, we're good. Perfect. There we go. And it's always just important just to double check that verification really quick. Make sure left-hand side equals right-hand side, and we're good. Okay, example 2. We're going to deal with one with an extraneous root. So again, we always want to check with our verifications, but we never know until we do that final check if there's an extraneous root. Now, I mean, it could be extraneous if it doesn't go with the MPVs, of course, but that's another thing. Now, from here, again, we want to factor this right away. So I'm going to factor this as we write our 4x minus 1 over x plus 2 minus x plus 1 all over x minus 2, which is equal to, in the numerator, we're going to factor this. So what multiplies to make 24, but then adds to make -4? I don't know if terms actually do this for us. Just looking at this, I'm like, so we could go down the list of, we have 12 and 2, we have 8 and 3, we have 6 and 4. There's really nothing that's going to combine to make this, so maybe we just leave it as this for now. It's x squared minus 4x plus 24. That's totally fine. If it doesn't factor right away, don't fret at that point, just kind of leave it. Then we're going to write this as x plus 2 and x minus 2 because we recognize x squared minus 4 as a difference of squares. Now, off on the top here, I'm going to write my MPV. So my MPVs are where x cannot equal plus or minus 2. If it's either plus or minus 2, it's going to eliminate the denominators. The other thing I want to state here is what my LCD is. The LCD is the combination of x plus 2 and x minus 2. And, it could be vice versa if we really wanted it to, but, in this situation, we're going to write it as this. Okay, x plus 2, x minus 2. Now, from here, we're going to multiply both sides by that given LCD, because if we've stated our MPVs, we can now move to our next step. So I'm going to surround the left-hand side in brackets. I'm going to surround the right-hand side in brackets, and we're going to multiply it all by this LCD. So I'm going to go x plus 2, and I'm just going to use red just to represent the LCD multiplication. So x plus 2, x minus 2. There we go. Let's do the same thing over here. X plus 2, x minus 2. Okay, and now once we've had it written on both sides, what we can do is distribute it into all the terms. So on the left-hand side of the equation, if we multiply the x plus 2, x minus 2, it cancels the x plus 2 for the first term, leaving us with the following. This is going to be 4x minus 1 multiplied by x minus 2. Then minus, we have our x plus 1. We can cross out our x minus 2's, meaning I multiply by the x plus 2 of that term. Okay, now on the right-hand side, if the x plus 2 and x minus 2 are shared in the numerator and denominator, this just leaves me with x squared minus 4x plus 24. No problem to us. Okay, we're going to expand the terms on the left-hand side here. So this is going to give me 4x squared minus 8x minus x plus 2 minus, I'm just going to put a bracket here just for now before I do any sort of distribution of that negative. I'm going to write this as x squared plus 2x, plus x plus 2. And then on the right-hand side, this is still equal to x squared minus 4x and then plus 24. Okay, Now, what we're going to do is we're going to combine our terms together. 4x squared minus x squared is 3x squared. We have negative 8 minus 1 x is negative 9x. Negative 9x minus another 3x's is negative 12x. And then we have 2 minus 2, which is just 0, is equal to x squared minus 4x. And then my last term was plus 24. Now, if we want to keep the x terms positive, we're going to bring all of the stuff on the left-hand side over, or all the stuff on the right-hand side, I should say. So I'm going to write it as negative x squared plus 4x minus 24. And we're going to bring that all over to this hand side here, or the left-hand side. This gives me 2x squared. I have negative 12 minus 4 is negative 16x. And then we have minus 24 because it's going to go with it. Excellent. Now, in our quadratic equations unit, we always factor out a GCF if possible, or divided by some sort of factor. In this situation, I may as well just divide by that factor of 2 and take it away completely. But I mean, I could just factor it as a general GCF, but I'm going to almost just get rid of it, because if it's just a numeric coefficient, why not? So we divide all the sides by 2, and if we divide all sides by 2, let's just do that quick here. So divide by 2 and divide by 2, because they're all divisible by 2. I get x squared minus 8x, and then plus 12 is equal to 0. Now, what multiplies to make 12 and adds to make 8? So we need to go through our factors here, or if this is even possible based on this situation. And I feel like there should be another negative here. Yes, in fact, the negative is right here. So we need to multiply to make negative 12 and then add to make the, let's just double check here. I want to make sure all my terms are correct based on this. Yes, seems good. We distributed that. We brought them over. Perfect. This is a negative. Yep, seems okay too. We added 4 from this other side. We added 4. That's right. So as soon as you kind of get that hunch, you should make sure that you're double checking this. If I added 4x from the other side, because it was negative 4x over here on the right, if I add it, that means that this needs to be negative 8 here. So I'm just going to change this to a negative 8, which means that if we divide it by 2, this should be a 4, which makes a lot more sense. I was going to say, I was like, we're kind of getting stuck on this not having factors. Now, we multiply to make negative 12 and add to make negative 4. This is x minus 6 and x plus 2, which is equal to 0, meaning my two solutions are going to be x equals 6 and x equals negative 2. Okay, now that we have two solutions, we just need to verify that these things actually both are solutions. To do that, remember, we just plug it back into the original and we can determine the extraneous root, or we can look at the NPVs, and I think that's going to be our easiest bet here. If you look at the NPVs, it said we couldn't have plus or minus 2. If it was plus or minus 2, it eliminates one of the denominators, or both sides of the equation here. We see that 2 of the denominators would go away. So we want to look quickly at this and be like, is this even a possibility? No. In fact, when we look at this, we want to circle it and write extraneous and put a line through it, because we look at this and we're like, there's no possible way that this could be it based on the NPV. Now, this simplifies our job a lot, because at this point, all we need to determine is if 6 is actually a solution to this equation, in which I will be very short with it. It definitely is with this one. So you can verify that afterwards and you can plug that in. For this situation, we just wanted to double check with our extraneous roots, and those come from typically our NPVs or checking that they don't work. But we always want to compare against our NPVs and just make sure that one or both don't work depending on the situation. All right, now let's move forward here to part B. So part B, very similar, pretty comparable to our last example. We want to again write this out in its most factored form. I'm going to write this as 3x over x plus 2 minus our 5 over our x minus 3, which is equal to negative 25 all over. The factored form of multiplies to make negative 6, adds to make negative 1, is x minus 3 and x plus 2, which, to no one's surprise, we should get the same factors just combined together. Now, what we want to do is we want to state our NPVs right away in the top. So our NPV is where x cannot equal. Our first one is negative 2. Our second one is positive 3. So if it equals either one of these, we're not going to be too happy with that. The next thing we want to do is make sure we state our LCD. So our LCD in this situation is the product of those two factors. It's going to be x plus 2 and then x minus 3. So as long as we account for that, then we're good. Now that we know our LCD and our MPVs, let's multiply both sides of the equation by the same thing. So let's multiply the left-hand side as such, like this, and maybe I'll just backpedal that just a little bit so it's a little neater. There we go. So on the left-hand side, we're going to go x plus 2 and then x minus 3. Same thing on the right-hand side, we're going to go x plus 2x minus 3. Excellent, there we go. Now we multiply these in each individually. If I multiply the x plus 2x minus 3 in, the x plus 2's in the first situation cancel, so this is going to give me 3x times x minus 3. Then my next one is going to be negative 5. The x minus 3's cancel. This leaves me with x plus 2 in the numerator, which is equal to, on my right-hand side, if they share the same binomials, then we're just actually left with the number, no more denominators. Now we're going to expand this. This becomes 3x squared minus 9x. My next term is going to become negative 5x minus 10 is equal to negative 25. Now we want to see if we can combine some terms here. This is 3x squared minus 14x minus 10 is equal to negative 25. And if we have our constant terms and all the terms, including the x squared, are positive on the left, I want to make sure I bring across this 25 by adding it. There we go. So this is going to give me 3x squared. And then this is going to be, and let's just make sure I'm using space effectively, 3x squared minus 14x. And then negative 10 plus 25 is positive 15, which is equal to 0. Now we want to factor this, but we're going to have to use some decomp because we can't factor it a common factor. So it's 3 times 15, which is 45. What multiplies to make 45, but then adds to 14? It's actually 9 and 5. So we're going to write this as 3x squared minus 9x minus 5x, and then plus 15, which is equal to 0. I factor this by grouping, so I'm going to take 3x and leave x minus 3. I'm going to take negative 5 and leave behind x minus 3. There we go. Now I'm going to pair together the 3x minus 5, or the outside terms, and 1 of the common binomial and write it together. Now what this means in terms of my x's is I'm just going to go up over to the right-hand side here. One of my x values is going to be x is equal to negative 5 over 3. And sorry, this should be positive 5 over 3. And then my other x value is going to be where x is equal to positive 3. Okay, now again, this is where you want to go right back to your MPVs. If you look at your MPVs, you're like, oh, we can't have 3, because if it was 3, then it's an extraneous root. So we want to make sure that we don't account for this, because if I use 3, then it's not actually going to end up being a solution, and it must be labeled extraneous, or else we are accounting for something that should not be included and in fact has some sort of gap in the graph, and we don't want to include this. And then our only solution in this case should just be the 5 over 3. If we have the 5 over 3, we're happy with this. We see this as a good solution here. And again, you may want to verify this and actually plug it into the equation directly, but in these situations, when we've already done so much algebra, sometimes that can be a bit of a nuisance at that point. And plugging in a fraction into multiple fractions or rational expressions, sometimes a little annoying. So we'll check with our MPVs, and then once we check with our MPVs, we typically will consider that okay for these here. All right, now another example here, we're going to want to solve this one here. So we see they both have x minus 4, which actually makes our MPV job really easy. It's already in its factored form. We say that x cannot equal positive 4. If x equals positive 4, it wipes out both those denominators. As well, we know that our LCD is actually x minus 4. So LCD is the x minus 4 we see. Excellent. If it's only one of them, don't worry about it. Okay, now from here, or I shouldn't say don't worry about it, it's just the term itself. Now, what we're going to do from here is we're going to take this and go, well, if we rewrite it as 5x over x minus 4 plus 2, and then this is equal to 3x plus 8 all over x minus 4. What I'm going to do is I'm going to surround both sides in brackets, as we've done before. So my left-hand side, my right-hand side, we're going to multiply both terms by the x minus 4, which represents the LCD. Perfect. Now from here, what we're going to do is we're going to multiply this in. So x minus 4 over x minus 4, this just leaves me with 5x, and then plus 2 times the x minus 4, because there's no denominator to cancel out here. And then this is equal to, on my right-hand side, the x min's cancel, and I get 3x plus 8. Now let's expand this a bit. This gives us 5x plus 2x minus 8, which is equal to 3x plus 8. I combine my terms on my right-hand side, or my left-hand side, I should say. Minus 8 is equal to 3x plus 8. Now, if I subtract the 3's from either side, here's what I find. If I look at this, I'm like, okay, well, minus 3x. Let's say I subtract it from this side, and then I subtract it from this side because I need to do what I do to one side, I do to both. This actually leaves me with 0 x's, and I get negative 8, which is equal to 8. Is this true? No. The left-hand side does not equal the right-hand side, and in this situation, if you do not get a left-hand side that equals a right-hand side, especially when you're just trying to solve for the x value, essentially what this means is that there is no given solution to this. So we just want to make sure that we're being very careful with this. If we ever get this type of situation, then just be very careful that this, oh, and actually, this is why we got to be very careful. I'm just realizing 5x plus 2x, a lot of you are probably like, wait a minute, where this is 7x. Yes, this should be 7x here. So this would be 7. Then when we minus 3, let's backpedal this. I was going to say that's a kind of an odd solution. If I minus 3x here, this is going to be 7x minus 3x, which is 4x minus 8 equals 8. We add the 8 to the other side. There we go. And then we end up getting that 4x equals 16. We divide both sides by the 4. And then therefore we end up getting that x is equal to 4. Now, is this a legitimate solution? What did we do before? We go up to our LCDs. Is this actually an allowed solution? No, because our non-permissible value, or the value we cannot use, is x equals 4. So we look at this and we're like, nope. We got to draw a circle around it, put a line through it, write ext, and we are completely satisfied with doing that because we know that this would end up having, it wouldn't satisfy the equation. Now, what does this mean? We need to be very clear. This actually means that there's no solution. So you can say, therefore, no solution, because there is no x value that satisfies this equation here. Perfect. That would be the appropriate thing to write with here. So no solution, or no root, or all roots extraneous, however you want to phrase that, you could use. Okay, we got one last problem, and this is kind of like a test-based one. What I'll do here is, you know what, I'll solve it just because, you know, it's in the notes and it's here, but I'll treat this as a challenge problem. If you're watching this for the first time, just make sure you pause the video at this point. The reason I say pause this video is I want you to have opportunity to try it on your own. So what we're gonna do is we're just gonna pull from here, and we're gonna pull this image in. Okay. What I'm gonna do is I'm gonna bring open a new page, and then in this question, essentially what they're asking for is, what is the extraneous root of x? So we're going to solve the whole thing through, and then we're going to figure out which root doesn't work in this equation. And that will most likely come from the MPVs, just like the ones above here. So let's use our template here. I'm going to bring in the image here. There we go. And I'm going to just paste it right at the very top, and then we're going to work directly off this here. Perfect, there it is. Okay, let's do this one together. So right away, we want to state it in its factored form. To state it in its factored form, it's going to look like the following. We're going to write it as 30x. Whoa, there we go. Okay, we're going to write this as 30x. Actually, and we should probably take out a factor here in the numerator. I'm just trying to think if that's going to make it better. I don't think it would. So let's just continue forward. I know we want to typically factor it in all ways, but I'm just going to only factor the denominator here. So this is multiplies to make negative 15, adds to make negative 2. Well, this would be x minus 5 and x plus 3, which is then added to 6x all over x plus 3, and then is equal to 4x all over x minus 5. Now, to nobody's surprise, we end up getting that the factored form of the trinomial is the two binomials put together. Now, from here, let's just make sure we establish our MPVs. So I'm going to write that right at the very top. Our MPVs are the following, where x cannot equal, first one being 5, the second one being negative 3. If x equals the 5 or negative 3, we see this as a non-permissible value, or that it does not satisfy the equation. It's going to be an empty piece of the graph. Okay, now from here, we want to also state the LCD. The LCD, we're just going to write off to the side here. LCD, this is x minus 5 and then x plus 3. It is the two binomials put together. Now, what does that mean? We're going to then go over here and write that in for both sides. So we're going to go on the left-hand side, on the right-hand side. Let's start off on the right-hand side. We're going to write in x minus 5 times x plus 3, not minus 3. I'm going to then go over to the left and write the same thing. And in fact, it looks like we got to create a bit of space for ourselves. So I'm just going to try to drag this all over. I hope it doesn't drag the picture with it, which it didn't. Fantastic. Okay, on the left-hand side, we're going to zoom in here, and we're going to multiply this by x minus 5, x plus 3. Okay, this is going to get multiplied to both terms. In the first one, because it shares the exact same binomials, we're only left with the numerator. So this is 30x plus 10. We then have plus 6x over x plus 3. The x plus 3's cancel, and this becomes 6x times x minus 5. Excellent. Okay, on the right-hand side, this is going to become the x minus 5's cancel. I have 4x times the x plus 3. There we go. Now from here, we're going to expand this. This is going to become 30x plus 10 plus 6 times x, or 6x times x is 6x squared. 6x times negative 5 is negative 30x, which is equal to 4x squared plus 12x. Now, we realize that the 30x's cancel over on my left-hand side, so I'm just going to put dotted lines through them, indicating that they go away. Now, what this is going to leave us with is we have 6x squared plus 10, which is equal to 4x squared plus 12x. I'm going to move the x squareds from the right-hand side because I know there's fewer of them there, and I want to keep those terms positive, so minus 4x squared minus 12x. Now from here on my left-hand side, this is going to give me not 6x, but 2x squared minus 12x, and then plus 10 is equal to 0. I realize they're all divisible by 2, so why not just divide all terms by 2? Now from here, once I divide all terms by 2, I get x squared minus 6x plus 5 is equal to 0. If I put this in its factored form, it's going to be x minus 2 and x, and it has to multiply to make 5, but then add to make negative 6. What this is going to do is we need to make it in terms of x minus 5 and x minus 1, because it has to make sure that it is double negative such that it gets back to the positive. There we go. And therefore, this means that either x is 5 or x equals 1. Now we just want to go check with our extraneous roots or our MPVs because they tell us which one's extraneous. They told us in the beginning x cannot equal 5 because if x equals 5, it wipes out denominators and makes these non-real, or more than non-real, they're actually not even defined. So in this situation, the extraneous root we're looking for is this one here. The solution to this problem is this, where x equals 5 is the extraneous root. We would write our ext right here, and in your numeric response, you would just write number 5, and then that would be it. The solution that actually does work is x equals 1. This is a valid solution, but x equals 5, this is extraneous, and so we can only determine this once we've fully factored, got rid of the fractions, or got rid of that rational expression, and we've narrowed it down to our specific x values. All right, at this point, I leave you for practice. On the previous page here, there is an outline of practice, or there should be an outline of practice on one of the following pages here. So just be looking for that, and then good luck with the textbook practice problems. I'll have some more supplemental practice problems for you to go through as well. All right, good luck.